All right, so we're going to continue, and we'll do the same thing tomorrow. I just have a list of expressions that I want to go through that are going to simplify down to something a little bit better than what we start with. And it's the practice of taking these expressions, recognizing that we have some identities that are similar that you can substitute, and it should make things easier. Not right now. No. Okay. But it is open, and it is something that you probably want to start soon, so it'll probably be due at least on Monday. What you guys want to kind of think about when you're doing all of these, and I'll give you some kind of rule of thumb type things to use as you're simplifying. I would not say that, when we say rule of thumb, is that written in stone? No. Okay, so it might change every once in a while, but it's a good start. It's a good set of steps to get you a start on these things. I think one of the things that you need to think about and have at your fingertips, hopefully in your memory, is these reciprocal identities. Okay. Now the fact that this here is true, and we can also write that tangent of x is equal to 1 over cotangent of x. That's awesome. Okay. And the same thing can be said for these. I can write cosine of x is equal to 1 over secant of x, right? So just because the text is giving me that identity, this one is also true. Does that make sense, everybody? So even though they're giving you a particular identity, understand that as long as you do some algebra to those things, you still get another identity. As long as that algebra is legal, okay? If you're allowed to do that. For instance, can I multiply both sides by sine of x here if I wanted to? Looking at this one. So can I say cosecant x times sine of x is 1? And there's another identity. All right, but that piggybacks off the idea. We know that those are reciprocals, right? And that's the definition of reciprocals. The product of two reciprocals is 1. So even though these are the ones they present you with, we can adjust them slightly to gain others. Okay. And I was starting off talking about this one, how that one is nice to know. It's useful every once in a while, but knowing that cotangent is this is much more useful. You're going to use this substitution a lot more than what you would use this one for. Okay, so as we're seeing cotangent, people want to say, oh, it's 1 over tangent. Yeah, but if I make that substitution, and a lot of the problems that we do, you're not going to get any nice information until you then make the substitution that tangent is sine over cosine, and you got 1 divided by sine over cosine, which just gets me cosine over sine, which is this substitution anyways. Okay, so this one's going to be useful. Okay, and then the other ones that are going to be useful right now are these three. Okay, and we've talked about those three actually incorporate or encompass a lot of other identities because you can do subtraction. Maybe that first one, let's subtract cosine squared from both sides. So I get an identity that says sine squared x is equal to 1 minus cosine squared x. Okay, that one is encapsulated inside there. And there are others that are encapsulated inside there. Does that make sense, everybody? Same thing can be said for this one. Same thing can be said for that one. Okay? So those are just things to think about as we progress through these processes. Now, these things, hopefully we know what these are, and hopefully we have an understanding of them and why they are what they are. But I would say if those get used, if we're going to do 30 problems, I would say you might see these things 3 or 4 times. Okay, so they show up a very small percentage of the time. So right now I don't want to focus on those. If we do see something like this throughout examples or throughout homework questions, we'll come back and reference this and talk through it again. But those are all fair game. Okay, and even as we do these problems, I think we talked about this yesterday. I guess not yesterday. When was the last time we were in class? Monday. And when we solve one of these or simplify one of these, like they're being asked to do, you're actually creating an identity. Okay. For instance, I think we did the first example, so I don't want to do that one again. Let's do this second one here. It says 4 cosine t tangent t. Okay. My kind of, and I'm not saying what I do is right, Okay, I just have found that it's a useful approach. It is one that I'm always going to be looking for powers that are bigger than 1. Okay, of my identity, of my trig ratio. Okay, and that should, if I see powers that are bigger than 1, it tells me a couple things. It tells me, hey, maybe I can make a Pythagorean identity substitution, or maybe I can factor. Okay, so those are two things that I look for a lot of times. If I can't find a power that is bigger than 1, I then start thinking, okay, let's change everything to sine and cosine, or let's rewrite everything in terms of sine and cosine. And that is actually a task or a kind of an outlet for you in all of these problems that you get stuck on. You should be able to change everything to sine and cosine, and then go through algebra. Okay. So if you forget an identity, don't recognize the substitution, you can always change things in terms of sine and cosine, and then do the order of operations that are being expressed in front of you. And if you do those correctly, it should all evaluate down to the same answer, even if we use substitutions. Does that make sense? Okay. Now, if I go that approach, I like that approach because I feel I'm pretty confident and comfortable with my rules of algebra. And if I'm not certain about a rule of algebra, I think I'm confident and comfortable enough with being able to develop just on the sides and scratch work that can verify whether a rule is right or wrong, or I can use my technology to help me do that. So those of you that are really good at algebra and confident in your algebra skills and have no problems with algebra, that might be an approach to get you through these a little bit quicker than using substitutions. It does not matter. Okay? And if you sit down and you think about it, using the algebra and that kind of stuff is ultimately using some substitutions. Okay, so we get really, really, really good at algebra with this stuff. Okay, so I see these, and like I said, there's no powers bigger than 1. So what I'm going to try to do is I'm going to change every single term up there, every trig ratio, so that can be written in terms of sine and cosine, meaning that I should not see tangent, cotangent, secant, or cosecant left over when I'm done doing that, right? So I'm going to take this, and this is 4 cosine t. Obviously, no change there. But tangent can be rewritten as what? Yeah, so we've got sine of t over cosine of t. Okay? And another thing that I think is maybe useful for some people is to realize when I'm multiplying that number 4 by that number, so can't highlight the way I want to, by that number, cosine t is just a number, right? Is tangent t just a number? So they're just not all integers, right? 4 is an integer, but cosine t and tangent t are not integers. But a number times a number times a number, can those numbers all be written over 1? I'm not going to write this one over 1 because it's already got a denominator cosine. I could put it all over 1. It doesn't make a whole lot of sense, I don't think, to do that right here. To prove my point that I'm just multiplying 3 fractions together, aren't I? And when I multiply 3 fractions together, if there's a number up top, like say I have 2 times 3 times 4, let's go 5, let's make them all prime. And then I have, I don't know, 5 times 7 on the bottom. I can multiply all that stuff out, get my 35 on the bottom, get my 30 on top, and then simplify, right? But what's going to simplify? What number? If this is 30 up top and this is 35 on the bottom, what number is going to divide into both those evenly? 5. So couldn't we just cancel those out in that stage right there? Or a factor of 1 there. So isn't that really what's going on here? Don't I have a cosine up top and a cosine on the bottom? Okay, so they're going to cancel out. Okay, and now I have, when they cancel out, obviously we just cross them out usually, but it leaves a 1 in place, right? Okay, because it's cosine divided by cosine, which equates to 1. So 1 over 1, 1 over 1, whatever, how you want to write that. So now I have 4 times 1 times sine. So that changes to 4 sine. And then on the bottom I got 1 times 1 times 1. And now we have our answer, okay? Because there's nothing else we can do with that, right? There's no more substitutions to make. There's no more algebra can be done. Okay, you're essentially done when you a lot of the direction you say simplify so the expression is left with one trig ratio. That's what we've done here. But you can have multiples of that trig ratio, so 4 sine t, 5 sine t, whatever. That's what we're looking at. Okay, so how can we determine whether we've done this correctly? We can use whatever program you want. Use your TI-83 for all, I guess, intents purposes, but I like Desmos for this process because of the way we can type it in. I like GeoGebra. However, GeoGebra, the way you type that in, it's going to look very much like you would on a TI-83 or 4. It doesn't convert right into math print. Once you're typing in, you have to hit enter, and then you see whether you've typed it in the way you want it to. It is still superior, I think, to the TI-83 or 4 because that never shows you in math print whether you've typed it in the way you thought you should or not. Obviously, with this one, it's not a big deal because it is just all, there's no division or anything like that. So you have that picture there, right? Okay, that's what we started with, and I'm always going to graph what we started with, and then I'm always going to graph what we finished with. And what do we recognize about those two curves? They're the same. Okay, so that tells me that when I started with this and I transformed into this, everything I'd done in between was correct. It worked. Okay, this is just a simpler version of that, right? It's like if I had 2/4, might as well write that as 1/2, right? It's simpler. Okay, what we just created, guys, is an identity. Okay, at every x value, do you get the same y value back? Yeah, that's what the definition of identity means. So, from here on out, whenever you see 4 cosine x, tangent x, you want to replace it with 4 sine x, feel free to do that. Okay? However, what do you think the likelihood of us seeing 4 cosine x, tangent x again in another problem? Yeah, it's probably pretty slim. So that's why we don't memorize that one. Okay? We memorize the 7 or 8 that I have up there on the whiteboard, but we don't memorize that one because it doesn't show up frequent enough. Okay? And that's with all these. Every one of these we do, we are essentially proving an identity. Okay? But a lot of times they're just so infrequent that it doesn't serve a valid purpose to memorize it. Okay? So let's do another one. I guess another way you guys can check to see if you've done these correct, I'll go ahead and use Desmos to do this, but you can do the same thing on TI-83, is that I would type in the expression that I'm trying to simplify, okay? And this could be at any stage throughout the entire problem, okay? Type in whatever I want, okay? Now I use just this a value, and then I type in what I think it should go to. And I think I should have simplified this to 4 sine a. And because cosine has a domain of all real numbers, tangent has a domain of all real numbers except for negative pi over 2, pi over 2, and then add pi to those k times. But I should be able to start evaluating these and see if those numbers that I get back are indeed the same, aren't they? Okay. Now let's just see what happens. Okay, so there we're getting an undefined value, right? Here we're getting the value of 4. And the reason for that is that when we started off, that tangent had division by 0 there, right? We have an issue. Okay? So I would just make sure that I don't plug in pi over 2 as an option there for it. That's not in that domain. Does that make sense? Okay. But every other value should work and evaluate and show that we made adequate substitutions. We made appropriate substitutions. Is it okay? Not as easy on the TIA 384. We don't have these sliders that allow us to adjust and see all those relationships like we have on the Desmos or GeoGebra. But on the TIA 384, again, all you gotta do is say I'm gonna make sure that I'm gonna go into radian mode. You can be in degree mode. It's fine. I'm gonna go 4 cosine, and then I'm just gonna pick a number. I don't care. Pick 2, and then tangent of 2. Hit enter. See what I get back. See, is that the same thing as 4 sine of 2? That same thing back. So it shows me that I've probably done it right. Okay. Now, there are situations you gotta be careful. That could just be complete happenstance that those two evaluated at the same spot, the value that I chose. So maybe I want to try. Okay, let's replace a 2 with a 3 or a 4. Do it a couple times. Does that make sense? With varying values, and if you keep seeing the same answers equating back to you, you've probably done it right. Does that make sense? Okay, I'm just trying to show you that there could be, and you really the probability of this happening may be very, very slim, but maybe I've got 2 graphs that aren't the same, but they do intersect, and just by happenstance, I chose the x value of where they intersected. Does that make sense? That would fit back the same y value. So that's why we want to check maybe a couple different values other than just 2, try 3, try 4, and that kind of stuff. Doable? Okay. And again, you don't have to do that at the end. You can do that. Maybe I'm uncertain about a substitution at the 3rd step of the problem. Do that there and see if that validates your substitution. Okay. Let's come down to this 3rd exam. Give myself a little bit of room here. It's not working. All right. So cosine cubed x plus sine squared x cosine x. Okay. And like I said earlier, kind of rule of thumb thing for me is to look at powers. And I see there's powers that are bigger than 1, right? So now my focus is directed towards the Pythagorean identities. Focus on sine squared x, cosine squared x. Focus on 1 plus cotangent squared x, cosine squared x. And tan squared x plus 1 equals secant squared x. Those are the ones I'm going to focus on. Now, the nice thing is I see cosine and sine. Okay, so that's going to maybe narrow my focus then down to this one. Sine squared x plus cosine squared x equals 1. Now, I can't make that substitution right now because I don't know that it's valid and I don't know where to put it. But there is some things that are going on here that we can kind of mess around with. For instance, if I had, let's just say I had like x cubed y plus, I don't know, let's just say xy. Let's go xy, let's go ay. What can I do there? If this was the algebraic expression that I'm provided with, what could I do to alter that a little bit? What do they both have in them? Both y. So you can rewrite this as y, x cubed plus a, right? Okay. So why can't I do that down here? This would be my first term. This is my second term. What do they both have in common? Cosine x. Let's factor that cosine x out. And a key thing to remember, and this is very, we said this all year, but this is very important and very helpful in this situation. When we're factoring, what operation are we doing? Division, right? Okay. So I'm going to take the cosine x out, but that means I'm going to divide each one of these things by that cosine x, right? So what's cosine cubed divided by cosine to the first? Cosine squared. And then what's going to happen over here? Yeah, you got factor on the top and a factor on the bottom are the same. So they just cancel and leave you with sine squared. What's cosine squared plus sine squared? 1. And obviously then that just leaves you with cosine x. Those two things are always the same. Whenever I see, from now on, whenever I see cosine cubed x plus sine squared x cosine x, I can replace with cosine x. They're the same. Now, how often am I going to see that? Probably won't see it again. Okay? But it is an identity. Does that make sense? Okay? Because if we were to graph those, cosine cubed x plus cosine x sine squared x. When it gives this kind of warning sign here, it does not know. Yeah, I guess it doesn't know. I don't know what that means, but I'm pretty sure it doesn't know that I wanted multiplication there. Nope, wrong. It's not allowing me to cube it, which it did last period, so I don't understand that. If it won't allow you to cube it, we can do this. Is that the same thing? Okay. I have seen times when I put that, when I don't put that multiplication there, it doesn't know what to do as well. So just kind of pay attention. It'll give you a warning that something's not typed correctly. But if I type that in, does that look just like cosine x? Okay, I got the red one and the purple one on top of each other, right? And they're always equal, so they're an identity. Okay. If I had this, if I would have simplified down to this, okay, you see how they don't overlap all the time? So if I started with this and I thought I got down to this, I thought this was my answer. If I graph them, they're not the same. They're the same sometimes, aren't they? Everyone here at 0, they're the same. Here, at whatever that number is, they're the same. They're the same there. So they're the same occasionally, but not all the time, right? And that's the thing that if I'm using my calculator to evaluate and check, I would want to check multiple spots, because what if I just choose an x value that just by chance was that x value there? They would equate, okay? So I'd want to check one next to it and one next to it, okay? Make sure that they don't equate or they do equate to validate my arguments. Is okay? Let's do... I don't want to do that next one yet. We'll come back and do that one tomorrow. Some easier ones before then. All right, so let's simplify. Cosine of x over 1 minus sine squared x. And we're going to be able to get this down to one expression, one trig ratio. And it's actually a pretty quick substitution that we can make here. I see, and again, this is going back to the last couple examples we've seen. Whenever I have a power of 2, I want to think about these Pythagorean identities. Now, I use that one because that's the one that uses these terms down here, right? You know, if it was 1 minus tangent, or sorry, 1, I guess it'd be 1 minus secant squared or something like that, then I would want to look at the one that has tangent squared x plus 1 equals secant squared x, okay? So looking at this one, can I transform this red one where it looks like that one. Can I take this sine squared x here and move it to that side? And that would leave me with cosine squared x is equal to 1 minus sine squared x, right? Do you see now that that is the expression that we have in our problem? What can I replace it with? Cosine squared. Okay. Now this is just to prove my point with you. I'm uncertain about that. I'm not sure that that was valid. So I'm going to start with the part of my problem that I know is true, that I know to be true. Okay? And we're seeing that graph over here. Okay? I'm going to type in what I just came up with as cosine of x divided by cosine, what was it, cosine squared x, right? And see that they are the same thing graphically, aren't they? So that proves to me that right now, these two things are equal. That is a true substitution that we've made. Now, what do you notice that can happen here? Yeah, because now I don't usually write this, and I don't think many people will usually write this, but cosine squared means this, doesn't it? And then now you can directly cancel those, and what would you be left with then? 1 over cosine, which I heard somebody correctly say, secant. Okay? Now, the debate is, which one do I use? Because the directions will say simplify so that one trig ratio is left over. Either one of those got one trig ratio left over, right? The hope is that you recognize 1 over cosine x can better be written as secant. Okay, we want to write as secant. We'll keep doing these. We'll work on a couple more of these tomorrow. Like I said, 7.1 is open. Another thing that I think is important for you guys to understand is these are a lot like proofs in geometry. Or if I give you something in geometry as a proof, could you and your neighbor do it differently? We'll still have the same right answer? Yes, that happens here a lot. Okay? Thank you. You too.